for the public profile, and it took longer for SnapBody, 5 units in this case, to retrieve her public profile. These differences between response times for the public profile of Ashutosh and Anya are somehow unexpected and susceptible for differential performance bugs. Example 2 is for apathy phobe, where a user reported that they had 2 very similar inputs, but for one it took 7 times more to respond by apathy phobe than the other one. When we profile the apathy phobe, we are observing there is a constant time behavior and there is also another nonlinear behavior. So this is also susceptible for differential performance bugs. Finally, and most importantly for the purpose of this talk, is for machine learning library, where a user of scikit-learn libraries reported that they observed significant performance degradation in applying regression trees with MAE criterion as compared to MSE criterion. And in this plot, you can see the performance time versus the size, where there are different modes in the response time. All of these challenges arise the question, how could we detect and understand differential performance bugs? They can lead to inconvenient services, waste hardware resources, and even cause security issues. It turns out that there are requirements. Requirement 1 is to generate diverse input, not just the worst case one. Existing performance fuzzers such as slow fuzz and pair fuzz focus on the worst case performance. They are looking for a single input that can cause huge degradation in the performance. Whereas differential performance bug may not necessarily manifest from the worst case performance. In the plot bottom, you can imagine that the differential performance bugs are manifested from mode 2 and mode 4. None of them are the worst case one. Therefore, we require to generate inputs to explore as many performance as possible. Requirement 2 is for debugging or profiling. Unlike worst case performance, where the user needs a single bad input to profile the system and find out what component contributes to that, in the case of differential performance debugging, the debugger needs to run at least 2 profilers at the same time for 2 inputs and compare the results to find out the root cause. In case if the debugger had multiple performance modes, they need to basically run multiple instances of profiler at the same time and compare the results. We cannot expect human analysis to do this manually. We need an automatic tool. All these challenges and requirements motivated us to develop a data-driven approach that combined fuzzing with debugging to address them. And this brings me to the second part of this talk, that is our approach. I show the workflow of our approach DFFuzz. Our approach has 2 phases. The first phase is to generate interesting inputs to manifest differential performance bugs. The second phase takes the inputs and further analyze them using features from the space of the input and program internals to localize and explain the root cause of differential performance issues. Let's focus on the phase 1 that adopts gray box evolutionary fuzzing to manifest differential performance bugs. So we have a simple representation of a program as a control flow graph. As we know, an input may visit a sequence of basic blocks, or you can imagine as a sequence of lines in the code. It may satisfy a condition such as condition C1 and took a loop few times until it reaches to the end part of the program. So we use a notion of performance as a cost, and it's represented as a number of lines executed. So this is similar to our performance fuzzers. But one important difference is in the model of the population. We consider a simple path as a representation for the population. For example, trace tau1 and tau4, they are from 2 different inputs and visit basic basic block 4 and 5 different times, as you can see, but they visited the same set of basic blocks, or you can imagine as a line executed. Thus, we put them in the same population, whereas the trace tau2 and tau3 are in different population. This is to be able to use this population to model performance functions. The second difference is for a group of population. In this control flow graph, input satisfy condition C1 and input satisfy condition C3 are in different paths and different population, but they have the same class of complexity. They are in the same group of the population. So in this case, in this simple control flow graph, we may have 3 populations, but we put population 1 and population 3 in the same group, and we use this information to focus on few groups of population with significantly different performance, as opposed to all possible population. Many of those may have similar performance characteristics. This concludes the fuzzing part. Let's move on the debugging part. So we take input from the fuzzing. We first do a clustering to basically detect different classes of performances. In this case, we obtain 3 clusters. The fact that there are multiple clusters lead us to the next step to explain them based on features from program input. So table 1 shows different features for different inputs such as tolerance, penalty, and solver, and we have labeled from clustering. One way to find a similarity and differences between the clustering is to use decision tree. In step 3, decision tree number 1 shows an explanation model based on the program input features. In particular, for example, it says that if the solver is SGD and the tolerance is equal to 0, then we are in brown cluster. Depending on this explanation, we may find some aspects unexpected. For example, the differences between tolerance become 0 and bigger than 0. So we take the analysis further using instrumented version of the program, and we generate internal traces such as method calls, function calls, or like condition statement calls. And we build or form table 2 that for each input shows like how many times a clustering for different inputs. Again, decision tree number 2 at step 5 explain the root cause of the problem. For example, it says that if the function f3 is called at least 1 time, depending whether function f5 is called 1 time or it doesn't call at all, we are in brown versus blue clusters. So this localizes the part of the code that most likely contribute to differential performance bugs. So this concludes the overview of this approach. Let's move on to the last part of this talk and illustrate experiments that show the scalability and usefulness. Perhaps scikit-learn is one of the most popular machine learning frameworks that supports various tasks such as classification, regression, and clustering. And logistic regression is one of the most important classifier inside scikit-learn, and it contains more than 3,000 lines of code in Python. So we start our process with fuzzing. We run the fuzzer for almost 2 hours, and we generate 185 functions, performance functions. So we consider 2 domains. On original program, we use a special computer to precisely characterize the response time. And then, as you can see, we characterize a performance function. Then we applied functional data clustering algorithms, and it returns 4 clusters, as you can see with different color in this plot. The fact that there are multiple clusters lead us to the next step to explain them based on program input features. So we apply decision tree on that space, and it provides us explanation. For example, it says that if we use different solvers, we will have different performance. So this is not unexpected. We expect that if we use different solver, we will have different performance. But the unexpected part is related to case where we have the same solver, but we ended up having two different performance, depending whether tolerance is 0 or bigger than 0. So we take that part further. On the instrumented version of the program, we generate the library's internal traces, and we have the corresponding cluster label using the clustering algorithms. Putting them together, again, we use decision tree to find out the discriminant model, and it pinpoints the condition inside optimized method. When we look at that part of the code, we are seeing the famous Newton iteration, where there is a condition, and that condition compared the calculated tolerance against the given tolerance by user showing with told. We observe that if the given tolerance told is equal to 0, this loop doesn't terminate, even if the compute tolerance is 0. So it's going to unnecessary call to calculate gradient and loss. We reported this, and they confirmed and fixed this issue, and the basically fix is to convert streak inequality to less than or equal. We also notice that the differences is related to two performance. None of them are the worst case one, in this case blue and black one. So we need this approach to find out this performance. We also perform multiple other experiments, such as on batch generator. We found out that it's possible that the batch size is float number and it causes huge performance behavior. It's also confirmed that has been since fixed by the developers. Another observation was for sample generator, where we reported two possible infinite loop iterations. The developers actually confirmed that issue as well, and they fixed this. But the interesting part of this fix is the rule of decision tree model that already tells the developers what they should do to prevent these performance bugs. We also perform on multiple other instances of libraries in machine learning. I also want to, and I encourage you to see the paper for the full result, and I want to also discuss a challenge we face. For example, in the case of regression trees, we observe that there is a quadratic behavior related to MAE criterion in the library as reported by the user, but we were not able to pinpoint exact location. The reason was that they were related to external libraries. Those we need to bring the source of information from those libraries and enable us to do more precise analysis. So we left this as a future work. I also want to emphasize that this is not limited to machine learning libraries. Here, in the case of Apache FOP, the user reported that for similar input, it takes 7 times more for one than the other one. We do this analysis and find out that depending on the compression type on the input image or the size of the overflow part of this image, we may have two different performances. So I also encourage you to see our AAAI 2018 about the fundamental of the clustering and how this approach is useful for Java web servers. In the case of SnapBuddy, that is also a Java web server, the users, Ashutosh and Anya, had different performances since they applied different photo filters on their public images. So we also basically explained, and this is also confirmed by developers. Finally, I also want to quickly mention that this approach is not limited to differential performance bugs. They can be useful to analyze side channels. For those of you interested in software security, I encourage you to see our NDSS 20 to see that how we adopt to analyze this issue. With this, I would like to thank you for your attention. The source code and the benchmarks are available on the following GitHub that you can find. They are already evaluated, and I'm happy to take further questions at this time. Thank you.
Thanks, Said, for the great talk. I really like the paper. So we have few questions. Michael Pradel asked, it seems most of your approach isn't specific to ML libraries, which is needed to generalize, what is needed to generalize the idea to other kinds of software?
Yeah, thank you for the question. I think this paper is mostly focused on the machine learning library, but the most important part for generalization is to define a size function that takes the input and says that what is the corresponding the size for that input. So as soon as you can define those size function, you can use the approach for general software. For example, in case of regular expression, number of star you have, the linear star is the indication of the size of the input. Or in the case of file, you may consider bytecode as number of bytes in the file as an indication of the size. So if you define this size for arbitrary programs, then you can generalize to any libraries or applications, I guess.
I see. Mm-hmm. Any other question, folks? All right, so I have a question. When you generate, what is your cost function when you generate new inputs in the fuzzing?
Mm-hmm. So that is number of lines executed in the program. That can be one, but mostly for this work, we use actual execution times from the library.
So for generating new inputs, you try to, you want to see that will maximize the difference of performance time?
Yes, so it's to find as many as possible clusters. So in other words, we are looking to find different cluster, and those cluster as far as possible from each other. So the user usually set number of clusters at beginning as a prior to the model, mm-hmm. and then it tries to find as many those number of clusters and with high differences.
I see. So one related question I was wondering, when you are generating the initial seeds, are they randomly chosen, or you also did something there?
No, actually, there's very limited initial seed, one input to start. So okay. You don't need to provide whole corpus or anything like that. So this approach will be able to find out new inputs. That is. So I also want to emphasize that here also size of input is more clear. That gives advantage for machine learning library as a model. So here is the size can be defined as a number of features times number of rows in the data set. Whereas in general software, it might be hard to exactly specify the size of input. So in the same line.
Okay, yeah, that makes sense. Okay, so thanks. Let's virtually clap, Said. And let's move on to the next talk, which is where Arnab will, from University of Paderborn, will talk about monotonicity of machine learning models. Arnab, you can start.
Okay, thanks. Hello, everyone. My name is Arnab Sharma, and I'm from Paderborn University, Germany. And today I'm going to talk about testing monotonicity of machine learning models. This is a joint work done with my supervisor, Professor Heike Wahem. First, I'll tell a bit about how machine learning works. So probably already all of you know this. Machine learning works in two phases. In the first phase, machine learning algorithm gets trained on training data. And after that, a predictive model is being generated. And to this model, if an input is given, it gives you an output class. Now this machine learning model is being used as a decision-making software in many application domains, ranging from social, economical, transportation, law, medical, and many others. Depending upon the domain of the applications, there are certain properties which need to be guaranteed for a machine learning model. And monotonicity is an important requirement in some specific cases. So let us understand with the help of an example where we might need to validate monotonicity for a machine learning model. Let's say that we have a machine learning model which is being used as a loan granting software, which is deciding that how much amount of loan should be given to a customer given the information of a particular customer. And the bank policy requires that a person with more income values should be given more loan. So if two persons come with two different income values, the person who has more income should be given more amount of loan. This is, by the way, is a kind of a monotonicity constraint, which is saying that the output of this machine learning model should be increasing with the increasing of the income of a customer. Now, maybe one way to guarantee this to use a kind of training example where you always have the monotone training example, but it has been seen that this will not guarantee to generate a machine learning model which is monotone. So hence, in this work, our goal is to develop a testing approach to test monotonicity for a given machine learning model. So what we did is we formally defined in this work monotonicity, and then we gave an approach to test monotonicity, which we call the verification-based testing approach. And we gave a unique distance metric for one of our baseline approach, adaptive random testing. And finally, we evaluated our approach on 90 different machine learning models. So first, how monotonicity can be formally defined. Let's understand the machine learning model, how it can be defined. So machine learning model essentially is a kind of a function which takes as an input set of feature values and gives you an output class. Now, monotonicity can be defined with respect to a kind of a particular feature. So let's say that we have two feature vectors, x and x prime. And x prime has ith feature value more than x, and we are keeping all the feature values for x and x prime as the same. And this should be the, if it is the case, then it implies that the output for the x prime should be more than the output for the x. So the prediction for the x prime should be more than the prediction of x. So this is essentially the monotonicity definition with respect to a single feature, but we extended this definition for a set of features and we define it as a group monotonicity. Next is our testing approach, which we call as verification-based testing. So it essentially consists of 4 important steps. So in the first step, we generate a white box model approximating the given given black box model. And in the next step, we verify the monotonicity of the white box model that we have generated in the previous step. And third, varying the counterexamples. What does it mean? I'll explain later. And finally, we improve the white box model that we have generated in the first step. So as I said before, first step is the white box model generation. Now, the main idea or the motivation behind this step is that we assume that the model that has been given to us is a complete black box to us. So we do not know anything about it. We wanted to generate a white box model so that we can apply some kind of known analysis technique to compute the monotonicity. So to this end, what we do is we first randomly generate a set of data instances. And for each of these randomly generated data instances, we get the prediction from the black box model under test. So essentially what we get is a set of label data instances, which we call as oracle data. And these oracle data will now be used as a training data to train a decision tree algorithm. And finally, we get a decision tree model, which is basically mimicking or approximating the black box model that we want to test for monotonicity. As I said before, the main motivation why we generate a decision tree model out of the given model under test is to be able to apply an analysis technique so to verify the monotonicity. So in the next step, after generating the white box model, let's say that we get a decision tree like this. And here, each of the leaf node is basically giving you the class. And let's say we have two features, contract and income. Now, next what we do is we convert this decision tree to logical formula. And this can be easily done if you encode each of the branch as a kind of condition and the leaf node as a implied class. After converting the tree to logical formula, we next add the non-monotonicity constraint and add it to the formula. So then the idea is to try to find out that whether whether we can find out that the monotonicity constraint is violated. So after adding this, what we do is we give this formula to an SMT solver, Z3, and Z3 then checks for the satisfiability. If it cannot find any counterexample for this logical formula, then we stop there. Although it might happen that there is the given black box model is still non-monotone. So essentially, this is a testing approach. For this example, the SMT solver will definitely give us a counterexample. And as I said before, we are computing the monotonicity on the decision tree, which is not the original black box, or which is not the model under test. So we call this counterexample as a candidate counterexample. First, I'll tell you about the last step, white box model improvement, and then I'll go to the third step. So after describing this step, it will be clear that why we need to have the third step. So after finding out, after getting the candidate counterexample, we check for the validity of the counterexample by using the prediction of the model under test. So if it is a valid counterexample, our job is done. We found a counterexample where the monotonicity is violated, and we say that the model is non-monotone. If we see that the counterexample is not valid, so it is not agreeing with the black box, the prediction of the black box, the model under test, then we add this add this counterexample along with the prediction from the model to the Oracle data and try to improve the decision tree by retraining it. But the thing is that if we just add these two data instances and their prediction and try to retrain it, it is really inefficient, because training is a costly operation, and training a decision tree just by adding two data instances is really inefficient. So what we'd like to do, we want to generate more counterexamples from a single counterexamples, and that's why we need the third step. So in the third step, what we do is we use two strategies, pruning of feature and pruning of branch, to generate multiple counterexamples from a single counterexamples. So let us understand this with the help of this same example. So first, the feature pruning technique. So what we do after finding out the counterexample, we store it, and then what we do is we add the negation of one of the feature values from the counterexample, add it to the logical formula of the previous from the previous case, and then give it to the Z3. So Z3 will now try to generate a counterexample where the contract one, the feature value is not anymore 11. So it will definitely give us another counterexample, and similarly we do the same for the other feature, income, add it to the logical formula, give it to Z3. And Z3 give us another counterexample where the income is not 40. So in this way, we do the same for this data instance, and we get multiple number of counterexamples just from a single one. Next is the pruning of branch technique. What we do here is we first find out that which are the branches responsible for generating the counterexamples. So in this case, these two are the branches where the counterexamples which cause these counterexamples. And after finding out the branches, we toggle it. So what we mean by that, let's say that we take this branch, and then what we do, we basically add the negation of the condition here. So the branch was this part of the branch. So we go like top down way. So we first take this part of the branch, toggle it, and add, so negate it basically, and add it to the logical formula, give it to the Z3. So Z3 will try to generate a counterexample where the contract one is not anymore greater than equals to 11. We go in the next part of the branch where we add this income one not greater than 39, add it to the logical formula and give to Z3, and Z3 will give us another counter examples. So we do the same for the other branch, and this way we'll be able to generate multiple counter examples from a single counter example. So this is a bit summarized version of our approach. So first, what we do, given a model to test for the monotonicity, we approximate the model by using a decision tree model and apply a verification verification technique on the decision tree model. We convert the tree model to logical formula, try to generate counterexample violating the monotonicity. If we find a valid one, we stop there. If we find an invalid one, we try to generate more. Next is the evaluation of our approach. There does not exist a testing approach to test monotonicity for any black box, for any machine learning model. So what we did is we took two baseline approaches. For that, one is a property-based testing approach called Quick Check for Python, and another is adaptive random testing, which we implemented by ourselves. And for the test cases, we took 9 machine learning algorithms from scikit-learn and 10 datasets from UCML and OpenML. So these are the machine learning model that we have considered for our evaluation. So essentially, this is the KNN with 10 models. And the interesting model one interesting test case was light GBM. So this is online available. You can basically enforce monotonicity constraint with respect to certain features. You can say that I want my light GBM model to be monotone with respect to some specific features, and then it is supposed to be monotone then. So this is the result of verification-based testing, adaptive random testing, and then property-based testing. So clearly here you can see that the verification-based testing is able to find out more number of cases than the adaptive random testing and property-based testing. One interesting find out was that the verification-based testing was able to find out supposedly the non-monotonicity in the supposedly monotone models. Next, we try to also look at that how efficient our approach is compared to the adaptive random and property-based testing, and we saw that our approach is quite fast, even though it involves a lot of trainings and SMT solvings. And we have performed more experiments, like we try to look at that how good our decision tree to approximate the black box model under test, and also how many number of failing attempts each of the approaches needed before it can encounter the failing test cases. And also we try to compare our approaches, our two pruning strategies to find out which gives us which gives a better performance. So if you would like to know more about our experiments, please have a look at our paper. Okay, so I am at the end of my presentation. To conclude my talk, I have told you about our verification-based testing approach. So our technique approximates the black box model by a white box model and applies SMT solving techniques to compute monotonicity on the white box model. And we have evaluated the effectiveness and efficiency of our approach by applying it to several machine learning models, and found our approach to be to outperform both adaptive random and property-based testing. As a part of our future work, we plan to apply this scheme to validate other important properties like fairness or robustness properties, because our white box model easily allows for checking other properties just by applying a different check on the generated SMT code. So thank you for your attention, and if you have any questions, please feel free to ask.
So thanks, Arnab. Audience, please, do you guys have any questions? Feel free to ask. And meanwhile, let me start. I have actually few questions. So first one is that what kind of domain have you tested? Like, what are the inputs of these models?
These models we have generated, actually monotonicity is quite studied in the machine learning area. So machine learning.
So I am asking, say, for example, whether it is image, text, other features, things
okay.
like that.
Okay, no, it's just a classification problem, just binary classifications, multi
Of what?
problem of, for example, we have taken data from bank adult income data. We have taken data from medical sector. So there are standard benchmarks available for monotonicity checking.
And then how do you ensure that this monotonicity is intended? Because the example you first gave about the income versus loan, I mean, this is a very classical problem of, say, fairness issues, right? Like,
Yeah.
so there may be monotonicity is not intended, but your experimental setup will detect it as a monotonicity violation. Have you considered that?
Yeah, actually, I mean, maybe you are right. For the test cases that we have considered, maybe those are not at all intended for monotonicity. But we just wanted to show that, okay, if someone needs to ensure monotonicity for a particular model or for a particular case, then it can be used because then then our approach can be used to test monotonicity for the model. I mean, for the test cases, yes. I mean, it might not be intended, the monotonicity. It might be the case that the monotonicity is not intended at all.
Okay, we have a question from Saeed. He's asking that, are there any limitations in your work associated with using decision tree classifiers?
The main problem that we have faced, that actually this is also reported in our paper, that sometimes decision tree is not approximating the black box model so good. So for example, there is this particular test case where the decision tree has very low accuracy and approximation quality was really bad. And it was not able to find out the non-monotone cases, whereas the adaptive random testing and probability-based testing could find out the cases. So yeah, I mean, the main limitation was probably with the decision tree, the approximation quality of the decision tree.
Any more questions? All right, let's all thanks Arnav. It was a very great talk. And okay, let's move on to the next talk. So our next talk is from Shaikhat Datta from UIUC, and he will talk about flaky tests in machine learning applications. Shaikhat, the stage is yours.
Okay, thank you, Mushaki. So let me know if in case you guys can't see my screen or cannot hear me. So let me get started. Hi everyone, I'm Saikat, and I'll be presenting our work on detecting flaky tests in probabilistic and machine learning applications. This is a joint work with August, Rutvik, Zekun, Aryaman, and Sasha from the University of Illinois at Urbana-Champaign. Machine learning techniques have found tremendous success in complex tasks in domains like computer vision, natural language processing, and even medical diagnosis. On the other hand, probabilistic programming has also been gaining in importance over the past several years. For instance, Uber is using probabilistic programming to model user behavior like time taken for a second trip. Facebook is using probabilistic programming to filter out fake accounts. Given such important applications, it is critical that we test the frameworks which power these kind of applications. However, testing in this domain is very challenging. The tests that developers write in this domain typically generate a small data set, then run the algorithm, and then check the outputs. However, there can be randomness in different parts of this process. Firstly, most machine learning and Bayesian inference algorithms are inherently stochastic in nature. Second, there can also be randomness in the data generation process and also the order in which the algorithm sees the data. Further, there is also a lack of strong test oracles, which makes it very hard to determine the expected output of the algorithm. All these reasons contribute to non-systematic testing, which eventually leads to flaky tests. So what are flaky tests? A test which both passes and fails non-deterministically, even for the same version of code, is known as a flaky test. So why is this such a problem? Flakiness makes a test unreliable. The developer can no longer trust the outputs of the test. Second, it also wastes developers' time spent investigating the failures. And third, it also increases the build costs because the CI, the continuous integration systems typically rerun the fails test. Flaky tests have also been identified as an important problem in several major companies, and all of them are trying to mitigate their impact. On the other hand, researchers are also studying flaky tests to determine the root causes, the impact on developer lifecycle, and also trying to find ways on how to detect and fix them automatically. However, All the prior work on flaky tests, it focuses on general software, and hence, algorithmic randomness does not show up as a prominent cause of flakiness in any of the previous studies. However, our empirical studies indicated that algorithmic randomness is a major cause of flaky tests in the probabilistic and machine learning domain. Let us now take a look at an example of flaky test from the Allen NLP library. This is a PyTorch-based library used to solve NLP tasks. Here we have a test for the DNN model for machine comprehension problem. The machine comprehension problem, it generates answers for questions in the context of a passage. However, the given test here is flaky. The assertion that we see here, it sometimes fails when we run this test multiple times, even for the same version of code. And as you'll see later, this is happening because of the randomness of the underlying NLP training algorithm. So we'll look into why this is happening and how we can detect such flaky behavior. But first, let me talk about the contributions of our work. In this paper, we conduct the first study on the nature of flaky tests in 345 projects, which include 4 probabilistic programming systems and machine learning frameworks, namely Pyro, PyTorch, TensorFlow Probability, and PyMC3. We found 75 flaky tests and studied them, which are spread across 20 of these projects. I won't go into details of the empirical study, and you can find more about them in the paper, but here let me highlight some important insights from the empirical study. First, 60% of these flaky tests are actually caused due to algorithmic randomness, which makes it a major category. And second, adjusting the assertion thresholds, like the one that we saw in the example, is the most common fix that developers choose to fix these tests. Motivated by these insights, we developed Flash, which is the first technique for systematically detecting flaky tests, which is caused due to algorithmic randomness in this domain. In terms of results, using Flash, we found 11 new flaky tests, out of which 10 have been confirmed by developers as actual flaky tests. Let us now jump back into the example and see how this test works. So in the first line here, this initializes the DNN model with a small sample data set and model parameters. The data set in this case would be basically a set of passages with related questions and answers. Then it creates the batches out of data and initializes the vocabulary. Then it runs one forward pass of the model on the input data, computes the metrics, and finally checks whether the F1 score is greater than 0. However, as we saw before, that this assertion is potentially flaky. Let us now understand why. So even though on the surface level, there seems to be nothing wrong with this test, there can be several sources of randomness here. For instance, this call to the forward pass of the model has 6 calls to the dropout function. The dropout function is a common technique used in machine learning training, which randomly zeroes out some elements of the input tensor with some probability p. Here p is 0.2. And as you can guess, this affects the neural network weights during every forward pass. So why do people use this? This is useful for regularization, and it prevents overfitting of the model. However, as you can imagine, this leads to different models in every execution of the test, which eventually leads to different accuracy, that is F1 scores in each run. And hence, the F1 score that we get here can be different in every run, and it can also be potentially 0, which makes this test potentially flaky. So can we detect such kind of flaky test? Yes. To do that, we introduce Flash, which is the first approach for detecting flaky tests in applications which use probabilistic programming systems and machine learning frameworks. On a high level, Flash takes as input a project and returns a set of potentially flaky tests as output. Flash focuses on tests which fail due to differences in sequence of random numbers generated by such applications. So in the example that we saw before, Flash runs the test several times using different seeds. And on the y-axis here, we see the different F1 scores, and it fluctuates a lot. And Flash actually detects a failure in this case where the F1 score actually goes down to 0. So how does Flash do this? And what is the secret sauce behind it? So this is how Flash works. It executes the test several times by setting different seeds for each random number generator, RNG, in each run. And in fact, some tests can depend on multiple RNGs. The example that we saw before, it depends on NumPy and PyTorch RNGs. Then it collects the samples of the actual values, that is the F1 score in this case, in the assertion from each run. Then it fits a distribution on the collected samples. And finally, it reports observed failures and also computes the probability of failure of the test using the distribution. Let us now take a moment to understand, why do we need at all this machinery to deal with randomness? Given that RNGs cause so much problem for testing, so why do we at all need them? And why can't we just set the seed in them, right? That is a natural question to ask. But as we'll see in the next slide, this may not be the best approach. So setting the seed actually could make the test deterministic, and this is not an uncommon practice, as we also saw in our empirical study on these projects. However, this can lead to several problems. First, setting the seeds makes your test dependent on the implementation of the underlying random generator, and any change in the implementation could break your test. Secondly, Any change in your code which makes a different number of calls to the RNG could also break your test. Second, setting the seed locks a sequence of values which are produced during the test execution, which means we'll miss other potential sequence of values which could have reproduced a bug. And we actually witnessed the phenomenon in our qualitative study on 2 projects, where we removed all the seed setting logic from the test and run Flash with them. And we actually found a bug in the geomstats project, which would have been hidden if the seed was always set. So now that we understand why setting seeds may not always be the right approach, and we know the high-level idea behind Flash, there are now 2 challenges that we must address to make Flash work. First, how do we actually determine how many times we want to run the test? So here's a simple strategy. Let's say we run the test n times, and we have some magic way to determine whether that is good enough, and rerun the test if it's not. This brings us to the second challenge, which is how to decide how many sample set minimum do we need before deciding to rerun. So let us first understand, why do we even want to run the test several times? So obviously, running the test several times increases your chances of observing an actual failure of the test. And using the different executions, you can get a set of samples and get a sense of the variance in the actual value in the assertion. And using that, you can then compute the distribution of values, which could help you compute the actual probability of failure of the test. In statistics, convergence tests are typically used to determine whether we have seen enough samples so that we can faithfully model a distribution with some amount of confidence. So let's say we use the convergence test as a measure of the goodness of the samples. And this brings us to the second question. So why is choosing n, that is a minimum number of samples, so important? So if we choose very few samples, it can lead us to wrong conclusions about the test. If you choose too many, then this can be a very expensive exercise, especially in the cases where running the test itself takes a lot of time. Unfortunately, there is no good way to determine this. However, the user can choose values from the trade-off space between the number of samples and the convergence threshold. That is the strictness of the convergence test. And for our evaluation, we use a minimum of 30 samples. So let's now understand the workflow of Flash and what are the main components. Flash mainly consists of 3 main components: the assertion miner, the test driver, and the assertion inspector. The assertion miner takes as input a project and gives you a set of candidate flaky tests to test for flakiness. So given a project, it searches for the tests which do approximate comparisons between actual and expected values. So what does it look like? So this means it looks for assertion patterns, which include, for instance, the Python assert, which compares 2 values A and B using some relational operators. Or it could also be some NumPy or unit test assertion APIs, which compare floating point values up to a desired precision level. So why do we want to look for these kind of assertions? So remember that we want to look for tests which are more likely to fail due to algorithmic randomness. And our empirical study indicated that majority of the flaky tests which are caused by algorithmic randomness typically contain this kind of assertions. Let us now move on to the test driver module. The test driver consists of 3 main components: the instrumenter, the test runner, and the convergence test module. The instrumenter takes the original test T and performs 2 steps. First, it sets and logs the seeds in each random number generator. And in this case, as we know that the tests that we had before, it depends on both PyTorch and NumPy, so we go and set the seed in each. Second, it logs the actual expected values in the assertion. Here, the actual value is the F1 score, and the expected value is 0. Moving on to the test runner. The test runner runs the instrumented test several times. And in each run, it collects the seed, the test output, and the value in the assertion, that is the actual expected value from each run. It keeps on collecting samples until the convergence score is below some given user-defined threshold. So how does the convergence test work? So let's assume we have the assertion of the form which says assert x is less than theta. And we want to estimate a distribution of values of x and compute the probability that x is greater than or equals theta, which is actually the probability of failure of the test. So we use the convergence test as a heuristic to determine how many samples do we want to collect, which is basically a stopping criteria. There are a few other alternatives, like the SPRE test and the decay inequality. However, the convergence tests are less expensive and can help us target different distributions. Among the convergence tests, we use a Giviki test because it's the simplest variant, and it does not have any assumptions about the independence of the samples collected. The Giviki test, it intuitively checks how different are different parts of the set of samples. For instance, it will check the difference between the mean of the first 10% and last 50% of samples. And this gives us an intuition as to whether we have seen enough samples to compute a distribution. For evaluation, we use a minimum threshold of 1.0 for the Giviki test. Now, how do we compute the probability of failure of the test? So let's say we have the set of samples X, and then we compute an empirical distribution D on the samples. The empirical distribution is typically defined with respect to observed samples, and the CDF, that is the cumulative density function, is defined as a proportion of observed samples which are below the given value. So here, the CDF of theta would give us the probability that X is less than theta, and then we can compute the probability of failure of the test, which is 1 minus of that. Moving on, let us now understand how the test driver works and how it combines 3 modules. The test driver works in this way. Let's say we have the instrumented test A dash, and we have the set of samples N. This goes as input to the test runner, which runs the test N times and gets all the samples, which then goes to the convergence test module, which says whether the test has converged or not, or whether samples have converged or not. If not, we go back and collect more samples. And if it has converged, then we send all the samples and the log assertion inspector, which computes the probability of failure and points us to the likely flaky tests. So let's see how this works on the given example. So in this case, Flash runs a test with different Cs in each execution. And on the x-axis here, we have the different test executions. And on the y-axis, we have the F1 score. And we see that it fluctuates a lot. And Flash decides that it needs 40 samples to decide about this test. So let's see how it reaches there and how it uses the convergence score. So let's say we start with 20 samples. And we compute the convergence score here, which comes out to be 2.14. And this is obviously more than 1. So we go ahead and collect, let's say, 10 more samples. And this is still more than 1. So we go ahead and collect 10 more. And finally, it's less than 1. And so we can stop here. And now we can use the samples to compute the empirical distribution, which we can represent here by the histogram that we have here. And using this, we compute the probability of failure, which comes out to be 2.5%, which is non-zero. And hence, there is a chance that this would fail. And so Flash actually also observes a failure in this case when it runs with some particular seeds for the NumPy and PyTorch libraries. And a key component of reproducing any failure in this domain is to have the seeds, and Flash can easily do that because it was already sitting and logging the seeds. So we reported back to the developers who agreed that this is indeed a flaky test. However, there was no easy way to fix it, and hence they recommended that we mark it as flaky. So marking it as flaky would just rerun the test on failure. So why does the convergence work at all, and why this is a good choice? The convergence test, it helps us explore most of the distribution of values and helps us build a more accurate representation of the variable being observed. And it forces us to collect more samples if there is some instability in the initial part of the collected samples. Moving on to the evaluation. We evaluate Flash on 3 research questions. First, how many new flaky tests can Flash detect in these libraries? Second, how do developers respond to the flaky tests that Flash detects, and how do we fix them? And third, how many old historically known flaky tests can Flash detect? In the interest of time, I'll just focus on the first research question, and you can find more about the others in the paper. In terms of methodology, we ran Flash on 20 projects. So these are the same projects from the empirical study where we found 1 or more flaky tests. And for each test, we ran Flash for a minimum of 30 times, and we used the convergence threshold of 1.0. So overall, Flash found 32 failures in these 20 projects, out of which we manually inspected and determined 11 of them to be actually flaky. And the other tests typically failed due to environment issues, like the requirement of GPUs or writing to similar files and others. So to fix 5 of these flaky tests, we sent 4 pull requests, out of which 3 were accepted and 1 was rejected. In the rejected case, the developers proposed a different fix than what we sent. We also sent 6 bug reports, out of which 5 have been confirmed an actual flaky test and are pending fixes. And 1 of them has been fixed so far, and 1 is pending developer review. So there are more details that you can find in the paper and some interesting stuff, like the details of the empirical study, how we evaluated Flash on the old flaky test, and the details of the qualitative study as well. And I encourage you to go and read about them in the paper. In conclusion, I presented Flash, which is the first approach for detecting flaky tests in probabilistic and machine learning applications. Flash combines statistical convergence testing and simulates different random number sequences to detect flaky tests. Using Flash, we have uncovered 11 new flaky tests in the web programs. We have open source implementation of Flash, which you can find using this GitHub link. And with that, this brings me to the end of my talk, and I'm ready to take questions now. Thank you.
Thanks, Shrikant. Okay, some questions are coming. The first is from Michael Pradell. He's asking, how does Flash distinguish flakiness due to RNG from other reasons of flakiness?
So how Flash works is it sets different Cs in the different random number generators. And typically how Flash works is, so given the test, right, you have some assertion in the test, which is doing some approximate comparison, right? And then what it does, it monitors the values in the actual values in the assertion and tries to figure that out. And then it points it to likely flaky tests. And then we manually inspect whether it's actually a flaky test, right? And in all the flaky tests that Flash found, so we determined 11 of them to be actually flaky, and it did not fail due to any other reason. The other reasons that we found are basically due to some mis-setup in the environment, right? So yeah, so Flash targets such kind of flakiness, but by itself it cannot distinguish, right? Because we have to manually go ahead and look what is the reason behind the flakiness.
Mm-hmm. All right, thank you. The next question is from Per Erik Strandberg, and he's asking, did your findings on flaky tests indicate bugs in the test cases or the underlying software, or both?
So actually both. So there were some cases where we had to go ahead and fix some logic in the test, like change the thresholds and things like that. In some cases, we had to go and fix the source code. So it was a mix of both.
And did you report both when you report to the developers?
Yeah, report both. Yeah.
Okay, any other questions? Great. We will like to thank Shaikat and a virtual clap because where we are right now. And before ending the session, Thomas Ostrand requested me that he will ask a question to Greg. I don't know, Greg, whether you are here, but anyway, Thomas, please feel free to ask question. You are muted.
He cannot unmute himself, so he would need to write it.
He can unmute himself now.
Okay, did I just unmute? Yeah, okay. It's okay, you're hearing me. So what I really wanted to do, I should have said at the end of Greg's talk, but I wasn't able to figure out quickly enough how to get the question put in. So first of all, I want to just really express appreciation to Greg for being so kind to give a shout out about our long ago work on comparing data flow and branch coverage testing. That's very nice. But the main thing that I want to say is about that. When we originally did that work, we were thinking we would do some real comparison of testing methodology and effectiveness of testing techniques. But by the time we finished, we really decided that the main purpose of what we were
Uh-oh. I'm Greg, I'm here, but it looks like Tom froze. Oh, you're muted, Baishaki.
Yeah, I think we lost him. His video is also frozen.
Yeah, I think he's, yeah. Well, I think he told me he was having some connectivity problems, so. Maybe he'll come back in a minute.
I mean, we can ask him to send you a mail directly.
Sure.
Oh, he's back.
He's muted again, though.
I am asking him to unmute.
Yeah, okay.
Thomas, we cannot hear you.
okay, is it, can you hear me now?
Yes.
Yeah.
Okay, sorry.
And Tom, I'm here, but you got cut off pretty early.
Okay, well, my connection has been so flaky all afternoon, for which I apologize. I should blame the company, I guess. Okay, in case anybody missed it, I'm very grateful to Greg, and I appreciate his mention. The key thing I want to say is that if you're doing empirical research, take advantage of all of the tremendous amount of open source software that's available now. Much more serious, really serious programs that are there that experiments can be run on, and they will be much more relevant to actual practice. And that's what's important. That's what we need. We just need continually doing these studies, more and more of them, to build up evidence that can, in fact, give us some real results that we can base serious decisions on and serious methods on. So that's it.
Yep. I completely
Again,
agree.
Thanks, everybody.
Yeah. Well, thanks, Tom. Thanks again for your contribution there. It's a big one.
Okay.
You
Okay.
bet.
Sure.
Yeah.
Sure.
All right, so I think we had three very well prepared and great talk. And with that, I would like to end this session of machine learning. Let's thanks again to the speakers, and we'll see you guys again in the next session.